Vectors and dot products. So there are two different ways that you can find the product of two vectors. One is called the dot product, and when you do the dot product of a vector, the result is a scalar. And when we represent dot product, we use the dot there. So vector A dot vector B, we read that as A dot B. Sometimes the dot product is also called the scalar product or the inner product. That usually depends on your textbook publisher or even what country you're in. Cross product results in a vector answer, and we represent a cross product by doing like an X there. So it's sort of like a cross. So that is read as A cross B, and it's also sometimes called a vector product. In this class, we are not going to be doing vector product, only dot product. So consequently, because there's two different ways to find the product of two vectors, you would never represent the square of a vector like this with the a squared or the parentheses, because it's not clear if you mean a dot a or a cross a. This is a lovely GeoGebra demonstration to show you about dot product and what it means. Somebody else made this. So what we have here is the two vectors, a vector v, vector u, and the angle between them is being shown in degrees. And then up here we have vector u dot vector v. So right now we can see that the dot product is -12. And up here at the top, they're showing you, well, really how to calculate the dot product, but I don't want to spoil anything, so I'm going to scroll down. So one thing I want you to notice is my angle right now is obtuse, so my dot product is negative. Okay, still obtuse, still negative. If I go right here, oh, it even changes colors. If my angle is acute, my dot product is positive. Isn't that interesting? Now you're probably wondering to yourself, I wonder what happens when the angle is exactly 90 degrees. What, wouldn't you know it? The dot product is 0. That's amazing. So let's summarize what we just found in that demonstration. If the angle between the two vectors is acute, then the dot product is positive or greater than 0. If the angle formed by two vectors is obtuse, then the dot product is negative or less than 0. And the big kicker is that if the angle formed by the two vectors is 90 degrees, then the dot product is 0. That's amazing. The two vectors that are perpendicular to each other are called orthogonal. These two statements down here are key. That's why they're highlighted in this lovely peach color. So the dot product formula is pretty simple. If vector u is u1 comma u2 and vector v is v1 comma v2, the dot product you find just by multiplying their horizontal components, multiplying their vertical components, and then adding them together, and your result will be a number. So we're going to take some time to try the dot product on here. Pause the video, try them on your own. So for the first one, we're going to have 4 times 2 plus 5 times 3. So that's 8 plus 15, which is 23. The second one, we have 2 times -1 plus 3 times 0, which is -2. And for the third one, 2 times 1 plus -1 times 2, which is 0. That means that these two vectors here are orthogonal. A few properties of the dot product. So this first one would look kind of familiar to you with real numbers. Vector u dot vector v is the same thing as vector v dot vector u. That's called the commutative property. Any 0 vector times vector v is going to result in 0. That's called the zero product property. This is your distributive property. So if you have a vector u times the sum of b plus w, then you can just multiply vector u times vector b plus vector u times vector w, or dot w, I should say. And this product, if you do the dot product of a vector with itself, this is kind of cool. You're going to end up with the magnitude of the vector squared. It's the squaring property. Don't have a fancy name for that one, really. And then this last property is the associative property with a scalar. So if you have a scalar times u dot v, then you can either do the scalar times vector u and then dot that result with vector v, because of course that's going to be another vector. Or you can take vector u and dot it with k times vector v. You get the same result. So pause the video, try these problems on your own. All right, let's have a look. So for this first one, I'm going to have vector u dot vector v. So it's going to be -1 times 2 plus 3 times -4. and then I'm going to square bracket there just to separate it from vector W. Notice there's no dot between the V and the W, and that's significant. You'll see why in a minute. So -1 times 2, that's going to be -2 minus 12, and that's just being multiplied times vector W. So this is now a scalar, right? -14 times vector W. So now you're just going to do -14 times vector W, which was 1 comma -2, and you get -14 comma 28 with the pointy brackets, like so. For this next one, let's do 2 times vector V first. So vector U dot 2 times vector V, so that's 2 comma -4. So we have vector U dot 4 comma -8, that's a vector with the pointy brackets. So now vector U, that's going to be -1 comma 3, that we're going to dot with 4 comma -8. So now we do the dot product. So that's going to be a -1 times 4 plus 3 times -8, which is -4 minus 24, -28. Let's talk about the angle between two vectors. So there's a formula for finding the angle between two vectors. In a separate video, I'll show you how to get to this formula from the law of cosines, in case you're interested. You don't need to know how to define the formula, but you do need to know how to use the formula. We have the cosine of an angle, and this angle theta will be the angle between vector u and vector w, is equal to the dot product of u and, I said w, I meant v. The dot product of u and v divided by the product of the magnitudes of the vectors. Crazy. So pause the video and try this one on your own. So I'm going to write down the formula first. We have cosine of theta is going to be vector p dot vector q divided by the magnitude of vector p times the magnitude of vector q. All the notation can get kind of messy. So we have the cosine of theta is p dot q, so that will be 2 times -1 plus -1 times 0 divided by the magnitude. Remember, is going to be the square root of the component squared, the sum of the component squared. So it's going to be 2 squared, so square, plus -1 squared, and then the magnitude of vector q would be -1 squared plus 0 squared. So that's we're looking at -2 plus 0, so that's just -2. And then here in the denominator, that's going to be the square root of 5 times the square root of 1. You can see it can get confusing whether this is a dot or a product or a multiplication, you know. So, but these are real numbers, so of course multiplication. So it's -2 over the square root of 5. And remember, that's equal to the cosine of theta. So theta will be the inverse cosine of -2 over the square root of 5. So you go to your calculator, make sure you are in degree mode, and you're going to get 153.43 degrees. That would be the angle between the two vectors. And the dot product, if we look back here, the dot product was negative, and we talked earlier in the video about if the angle is obtuse, then the dot product is going to be negative, so that makes sense. Now, we talked about how to determine if vectors are perpendicular. That means that the dot product would have to be 0. Remember, perpendicular means orthogonal. But how do we know if two vectors are parallel to each other? Actually, you already know how to determine if two vectors are parallel to each other, because we talked in earlier videos about parallel vectors are just going in the same direction, but they don't necessarily have the same magnitude. So you can just do a scalar multiple of one vector equals the other vector, and then, or I should say, if one vector is a scalar multiple of another vector, then those vectors are going to be parallel, because the scalar would just change the length of the vector. It would not change the direction of the vector. So pause the video, try this one on your own. So we want to determine if these two vectors are orthogonal. Remember, orthogonal means perpendicular. So let's just find their dot product. So we're going to do 2 times 6 plus -3 times 4, 12 minus 12. Holy smokes, people. They are, in fact, I don't know why I circled the 0. The question is whether or not they are orthogonal. Yes, they are orthogonal because their dot product is 0. Orthogonal. All right, this one is asking which one of these vectors is parallel to this given vector. Now, this vector is written in unit vector form. If you prefer component form, that would be pointy bracket, 1 comma negative 2 pointy bracket. And so you want to figure out which one of these vectors would be a scalar multiple. So if I look at vector A here, and this vector u is 1 comma negative 2, and this is 2 comma negative 4, hopefully you can see that if you were to just double vector u or multiply it by 2, you do get 2, whoops, didn't mean to do that. Now I just spoiled it. You know, this is the last example. So that one is, in fact, a scalar multiple. Looking at vector B, you've got negative a half I plus j, or in other words, if you prefer component form, that would be negative 1/2 comma 1. And these numbers are exactly, if you multiply the original numbers by negative 2, you get these numbers. So yes, B is also parallel to vector u. Now, if you looked at vector C, this one is not parallel to vector u because the signs are the same. These are both positive numbers, and you need the signs to be opposite numbers. Vector D, same problem. The signs are both negative, and you need them to be the opposite in order for them to be a scalar multiple. But vector F, oh, the signs are the opposite. Would this work? Let's see. Can I get a negative 20 and a positive 10 if I multiply? No, that's not going to work because if you multiply by 10, you have the opposite there. So F doesn't work. Vector V, yep, that's a pretty easy one if you multiply by negative 100. So vector V is parallel to vector U. And then looking down here at vector W, that's not going to be parallel because they're both positive.